Hey guys, how you doing?
Good.
Good. Nice to talk. Nice to see you. Oh, oh my God. The penultimate experiment, ladies and gentlemen. The penultimate one. Only one more after this. To be fair, ladies and gentlemen, to be fair, ladies and gentlemen, next week's experiment is going to be kind of a workshop, and it will take a little bit longer. I'm dealing with Vesper and I'm dealing with Lewis dot structures. So that will take a little bit more time next week. It's your show next week. If you feel like showing up, that's fine. I'm not going to take attendance next week. But if you have any problems with doing Lewis dots or Vesper, I would suggest getting in here, okay? Anybody have any questions? Charlie, I would like to see you after class, okay?
Okay, no worries.
All right. Somebody remind me. Somebody remind me. Saki, it's your job. Somebody remind me to go over to look through the final with you at the end of the period, okay?
With me?
Yeah, everybody. Somebody needs to remind me. Just say final. When I start to say, okay, goodbye, yell final out at me and I'll remember, maybe, possibly. Okay? Because our final is in 2 weeks, guys. 2 weeks. If you're going to miss any period, that is one you should not miss, because I do not know whether it can be made up. So make sure 2 weeks from today, you have blocked off that bit of time. You are going to be here to take the final during that period. Okay, on to boiling. Guys, I have no life, ladies and gentlemen. I'm a chemist. I have absolutely no life. That's why I get to do some interesting things like watch water boil. Anybody watch water boil ever?
Sometimes, but it always seems to take longer when I do.
Yeah, you know, it's amazing. You look at the water as it's heating up and you see these tiny little bubbles down at the bottom, right? And you kind of get yourself excited that, hey, maybe it's not going to take as long as I think it's going to. But no, it takes forever, because you know what the little bubbles are? Anybody have any idea? The little bubbles, when you first start to heat the water, everybody's seen them. Anybody know what those are?
Gas bubbles?
Absolutely. Water dissolves gas. There's oxygen. If there wasn't oxygen in there, fish would die. You have oxygen, you have nitrogen, you have little gases in there. So what has to happen is we have to raise the temperature. As we're raising the temperature, the gases are going to go first. So that's what those little bubbles are. Now, basically, we all know about vapor pressure. We're Floridians. We know, we live it. We walk through this drenching madness every day, every time we step out. I mean, there have been times when I have felt wetter outside the shower than inside the shower. We swelter because of the phenomena called humidity. So we know that water evaporates into the air. Now, Basically, the amount of humidity that gets into the air is affected by variables. Two of the most prominent are temperature and pressure. Basically, the hotter the day and the hotter the pressure, the more humid we feel. So basically, the hotter the temperature, the more we are evolving water into the air. Is this kind of making sense, guys? A little bit, possibly.
A little bit.
All right.
Did that say Floridians?
Yeah, that's Floridians. Says it right there. I even spelled it right. Amazing. It's amazing what spell check will do for you. So what is boiling, guys? You get this water, you get this pasta water going, and you get these bubbles happening. What really is the definition of boiling? It's nothing more when the liquid vapor pressure equals the external pressure. Because when it equals the external pressure, you no longer have a liquid, you have a gas. And that's what happens when you're boiling. So basically, you got to increase the temperature enough so that the water vapors evaporate enough to increase the water vapor pressure to the same pressure as your barometer reading. That's what boiling is. So, what were we doing? Let's physically think about what's happening when we're boiling. When we're boiling, aren't things getting a little more excited than if we have the water just sitting there? We're putting temperature in there. We're getting things to whirl back and forth from one another. But we have energy that's going in there. Now, you have to understand that there's something that makes a liquid, a solid, and a gas. And that is something called intermolecular forces. How many of you have Dr. Musgrave? I see Max is there. Max, where are you at right now in lecture? Are you've gone far past all this stuff? You're right, probably dealing with solutions right about now, right?
Sorry, no. I've had them. I misunderstood.
No. Does anybody have Dr. Musgrave right now for Chem 1?
No.
Nobody? So basically, I've got virgins out here. In other words, nobody has heard about intermolecular forces before. Have you heard the term intermolecular forces?
Yes, I have.
Okay, Charlie, is it in connection with what you're doing now or with something you previously had?
If I recall, it was relatively at the beginning to middle of the semester.
Of this semester?
Yes, but I also could be wrong.
It doesn't matter. It really doesn't matter, because really speaking, you are going to get influxed with this tremendously at the beginning of Chem 2. It's the intermolecular forces of the first chapter. And basically what it does is intermolecular forces are the forces between different molecules. Intramolecular forces are the forces within the molecule. It's kind of like what keeps a oxygen and a hydrogen bonded in water. That's an intramolecular force. An intermolecular force would be the force between one water molecule and another. Easy way to remember that is, how do you travel between states? If you're driving, what kind of roads are you on between states?
The interstate?
Interstates. Interstates. In other words, we're going between states. So intermolecular forces are the forces between different molecules. And because we have these intermolecular forces, we can make something that is a gas or something that is a liquid by the amount of interaction one molecule has for the other. Now, there is a battle that goes on. The first battle is the intermolecular forces, which want to keep the molecules together. The other is the energy that's applied to the system, which wants to break the molecules apart. The more energy applied, the more the molecules want to break apart from one another. And if they're independent, they're acting more like gases. If there's less energy, then they're closer together. Then we have something acting more like a liquid. Okay? A liquid has a certain volume, but an unfixed shape. Gas, no fixed volume, no fixed shape. And we get all the way down to solids, we decrease the temperature low enough, then we have solids which have a fixed, rigid structure and a fixed volume. This all has to do with the intermolecular forces. And another thing you want to put back in the back of your head, intermolecular forces intermolecular forces cause physical properties. They cause something to be boiling at a higher temperature or a lower temperature. Intermolecular forces cause something to be very dense or not so dense. Intramolecular forces cause chemical properties. Is this kind of making sense, guys? So when we have these intermolecular forces that are acting on each molecule, all right, if I'm putting energy into my system, what's happening? That energy is going to break these intermolecular forces. Bottom line, all the energy is going to break the intermolecular forces. None of the energy is going to raise the temperature at that point. And that is why if you get to a boiling point or a freezing point, the temperature stays the same. Because if we've got any energy in, it's going to break these intermolecular forces up. And as long as I have liquid in there, there are going to be intermolecular forces. So we break all those first. Then once we get a gas, then we're able to raise the temperature. Is this kind of making sense to you guys? A little bit, possibly, maybe?
Yes.
All right. Now, again, I have no life. That's what causes me to look at things like thermometers when water's boiling. If you look at a thermometer while water is boiling all around it, as long as there's water down there, the water's heating up, going up to the thermometer, kind of condensing on there. When the drop gets big enough, it collects, it overcomes gravity and comes down to the very tip of the thermometer and drops off. While this is happening, we're getting a constant flow of that temperature, and the temperature stays the same. The temperature is not going to go up until all the liquid is in the air. And in order to do this, what has to happen is the pressure of the vapor from the liquid has to be equal to atmospheric pressure. So there are 2 points I want to make from this. One is important for an equation we're going to deal with in a few minutes, and that is at boiling, the pressure of the liquid equals the pressure of the atmosphere. That's the first thing. And the second thing is at boiling, the temperature does not increase. All right. Now, we can relate vapor pressure and temperature. through an equation called the Claussius Clappeyon. All right. If I was looking at this, if I was directly relating the vapor pressure, the vapor pressure would be equal to B times E, the natural log base E, raised to the negative delta H over RT. That's the original equation of the Clausius Clappeyon. But you remember I said a while back, chemists are famous for changing these whole bulky equations into something that looks like the equation of a line. Let's look here. If I consider that my ln of P is my y variable, and I consider my 1 over T is my x variable, can I measure pressure? Can I measure pressure? They do it on TV every night. The weatherman talks about the barometer pressure. Can I measure pressure, guys?
Yes.
Yes, you can.
Can I measure temperature?
Yes.
Yes. You can.
Can I measure the heat of vaporization?
Yes.
The amount. Can I actually measure the amount of energy? Can I do it easily? The amount of energy I need to vaporize an entire mole of a sample. Can I do that easily?
No, which is why you need the
probably not
equation.
easily.
So what I've done is I have manipulated equation. I've got two things I can measure, pressure and temperature. I've had to manipulate them, but I've got them and I've measured them. I can now make a graph where I can plot the ln of my pressure versus 1 over the temperature, and I will get a line. When I get that line is going to have a slope to it. And my slope of the line, stop it. Slope of my line is going to be equal to negative my heat of vaporization divided by R. Okay. One other point I need to make about the, nope, sorry, never mind. Never mind. I'll get to this in a second. Anybody, are we okay? Are we okay with this now? All right. We have to introduce something new to you here. Up to this point, you've probably never had to use a number other than 0.08206 for R. Am I correct there? Remember, I said way back when we were doing the gas laws, R only equals 0.08206 if the label for R is liter atmospheres per degree Kelvin mole. You change any of those parameters, you change the number itself. Now, we have to apply a different R to this formula because we're dealing with joules. Energy, heat of vaporization is energy. We're dealing with joules. So the value for R has to change to 8.314 joules per mole times K. All right, another thing you need to be aware of. The value, all enthalpies are reported out in kilojoules per mole. So if you are going to employ this formula, you need to either change the enthalpy from kilojoules to joules, or you have to change the R from joules to kilojoules. So that's part of the experiment we're going to do today. You're going to have a table where you have all sorts of vapor pressures at different temperatures. So you're going to take this table and you are going to turn all the pressures into ln of the pressure. In other words, you're going to get your calculator, you're going to hit the ln key on your calculator, type in what the pressure is, then hit enter, and that's going to be one column of your data table. You're going to take the temperature and you're going to take 1, divide it by the temperature, and you're going to fill out another column. Then you are going to use an Excel graph where you plot the values you have for ln of p versus the values you have for 1 over t. That will give you a straight line graph. The straight line makes a slope, and that slope has a value of negative heat of vaporization over R. Questions about the theory behind this, guys? Anything?
No.
No.
Okay. If we happen to measure 2 points, we happen to measure 2 temperatures, and one of the temperatures happens to be the boiling point. Well, if I do 2 temperatures, what I can do is I can subtract one of these equations from the other. When I subtract one of them from the other, I get rid of the lnb term. And that works out to be the equation you see below here. The pressure at temperature, at some temperature, ln of some pressure, vapor pressure at some temperature divided by some other pressure at some other temperature is equal to the heat of vaporization divided by R times 1 over the temperature of the top pressure minus 1 over the temperature of the bottom pressure. You have to keep them in this order. If you change the order around, then things can get kaflooey. And I'm saying that now, and I'm going to show you how you can change it in a second or two. What this equation means is the natural log of one vapor pressure over the other vapor pressure is equal to negative the heat of vaporization divided by R times 1 over the temperature at which the vapor pressure is on top minus 1 over the temperature at which the vapor pressure is on the bottom. Are we good with this formula? We understand it? Now I'm going to futz things. The reason I'm going to futz things is because you will see this in different forms. I can mathematically manipulate this. Stop it. Those two equations are the same. This equation all these three equations are mathematical manipulations. That's it. So I would suggest that you grab one of them. You grab one of them and you hold on to that one. Make sure that you know the exact place of the P's and the T's so that you don't futz this up in the future. So what we're going to do with one of our experiments, we're going to heat a liquid up to boiling. We know the vapor pressure at that point. It's atmospheric pressure. And what we're going to do is we're going to ask, well, what's the vapor pressure at a second temperature? We're going to have T1 and T2. One of these pressures is going to be associated with the boiling point temperature. We're going to use that as well. We're going to know delta H. Everything's going to be there except the other pressure. So, the experiment itself, you're going to shove some of the liquid into a test tube. You're going to fit a test tube through a rubber cork, and you're going to put the thermometer in the test tube, and you're going to put the test tube in a water bath. You're going to heat it slowly. And what you're going to do is you're going to watch. Remember I told you at the boiling point, the temperature doesn't rise? Well, the problem with that is you've got a lot of crap going on. And you've got this condensation, you've got this heating up. So it's hard to really detect the exact boiling point. And as a matter of fact, you usually generally figure out a range. When we did our experiment, ours boiled in the range of 61 to 69. So what I'm going to do is I'm going to take the average of that range. So I'm going to take 65. And I am going to look at the table on 117 of your lab manual. There is a table of about six compounds. In the table, there is a listing of boiling points. The table will identify not only the boiling point, but it'll identify the compound, and it will also identify the heat of vaporization. So we have a temperature, a delta H, and an R value at this point. We also know when it's 65, it was boiling. So the atmospheric pressure is equal to the boiling, the vapor pressure. So now I'm going to employ my Claussius Clappeyon 2-point. What we're asked to do is, we know the vapor pressure at boiling is atmospheric. What's that vapor pressure going to be at some other temperature? And we're going to designate it just for kicks and giggles as 295. So I'm going to plug my values into my Claussius Clappeyon. My 760 is associated with my 65, which is my boiling point of my methanol. The 125 is what I want to find out what the pressure is. 35.30 kilojoules per mole is the heat of vaporization of methanol. Notice I changed it from kilojoules to joules in order to reflect the value of R being in joules. So I do the math out to this step. I do all this math out. This ends up being negative 1.83. Now, when we get to this point, that is why, that is why he asked the one question in the pre-lab. Damn it. Stop it. Do what I want you to do. Thank you. Now, the question in the pre-lab was something like this. Do you remember that question, guys? Do you remember the question?
Yeah, I do.
All right. In order to solve this, guys, if you've had logs, bear with me. Unfortunately, some people have either not had logs or they had them so long ago that they've forgotten. What you have to understand is that if I have 10 raised to a regular log, 10 raised to the log of x is equal to x. In other words, 10 raised to the log is equal to 1. Can you accept that, ladies and gentlemen? Come on, give me some word. Can you accept this math, ladies and gentlemen?
I
Yeah.
think.
All right. So, a corollary. When we have log, the base is base 10. When we have ln, the base is small e, which is equal to 2.71 da. Okay? So if I want to get rid of the ln in this upper expression there, what I have to do is I have to raise this to the exponential power of e. I can do that. I am allowed to do this is going to get a bit funky. Yeah, good. It worked. But guys, if I raise the left side to that exponential power, I have to also raise the right side. So do we understand that, guys? We understand that?
Yes.
Now, e to the ln is equal to 1. Correct?
E to the ln is equal to 1?
Yes.
Yes,
So
I believe that's
basically,
correct.
e to the ln, that causes that portion of the expression to go away. And I got a divided by b is now equal to e raised to the c power. Does that make sense, guys?
Yes, it does. Thanks for going over it again.
So we have basically solving for a, we have, stop it. So solving for a, we get that. what happens? You guys see something like E. Let me see how I need to. You get ln A divided by B equals C, right? What you guys want to do is you want to take this and go ln A is equal to B times C. That is wrong because it's the ln of the quantity A divided by B. Does that make sense to you guys? The right part of this is wrong. The left part is how you really solve for it. Do I have any questions about logs?
Nope, good to go.
Good to go?
Good to go.
Okay, again, if this was overly simplistic for you, I apologize. If
No,
I
this
went
was
into too much
fantastic.
detail. Good. I'm glad because it's something you go over. Dear God, I think I went over it in 8th or 9th grade. So literally speaking, when I had to come back and teach chemistry again, I had to relearn this myself. So, you forget crap.
Yeah, and this is also beneficial in case like you're tired, you're just exhausted. I can go back over the video and just rewatch this part. So thank you for going over that.
My pleasure. Okay. All right. We're done. Half of the experiment is done, guys. Next thing, we're going to use the 1 point Claussius Clappeyon, which is the ln of P vaporization is equal to minus the heat of vaporization divided by R times 1 over T plus B. On page 120 of your manual, you're going to find the data. You're going to find vapor pressure data versus temperature data. Again, like I described earlier, you're going to have to take all of those pressures, and each one of those, you're going to have to get on your calculator, hit ln, type in the number, enter, write it in the column. For each one of the temperatures, you're going to have to put 1 divided by, type in the temperature, enter. So you're going to have 2 columns of numbers. One's going to be the ln of the pressure. The other is going to be 1 over T. Then what you're going to do is you're going to go to Excel, or God bless you, if you want to do it by hand, God bless you. You're going to go to it, and you are going to go to Excel program, and you're going to create a graph. Now, the graph you have is going to be of a straight line, but it's going to have a negative slope. All right? Make sure when you're doing this that you include the negative portion of the slope, because when I go to look at my slope, this is the equation of my line. My negative delta H over R is going to be equal to my slope. So I'm going to take my slope, which is negative, multiply it by negative R. That will give me the heat of vaporization, but you got to remember the heat of vaporization is going to be in joules. Because it's in joules, you have to multiply it by 1 kilojoule over 1,000 joules to turn it into kilojoules per mole. I've got a graph here, an Excel graph. My slope is equal to negative delta H over R. M times a negative R is equal to delta H. This should be the value which it, stop it. Oh, it is there already. That should be a negative value. So I'm multiplying 4,036, which is my slope, by my R value. This is going to give me my delta H, but you got to realize my delta H is in joules. I got to convert that to kilojoules. That's basically it, guys. I want to go through where you find stuff. And possibly the final. I just want to kind of basically reassure you about the final. What am I doing? I'm going to lab manual. There we go. It's going to take a couple seconds to load up. But this is where you're going to find a lot of the information that you need for this particular lab. Once you see the lab itself, it's not that involved. Fairly simple calculations. All you're doing is plugging it, chugging and plugging. Okay. Remember I said page 117 was the chart? So what you're going to be given in the data, you're going to be given a boiling point range. You got to match that boiling point range with your compound and the heat of vaporization. You're going to need this for the first part of the experiment, which is the two-part CC equation. So that's where you're going to get the heat of vaporization. You're going to know what the boiling point is, convert that to Kelvin. Whatever the boiling point is in Kelvin, you associate with 760, which is atmospheric pressure. Or if they give you another pressure in the data, use that instead for being atmospheric pressure on that particular day. We'll check on that in a second. All right, so you're going to have one pressure, heat of vaporization, R, and both temperatures. Solve the 2-point CC for the pressure. Now, if the pressure goes down, let's think logically here. I'm sorry. Let me erase that. We're thinking logically here. If the temperature goes down, what should logically happen to the vapor pressure? Should the vapor pressure go up or down?
Could you repeat the question?
If the temperature goes down, what should happen to the vapor pressure? Think about it, guys. Is it more humid on an 80-degree day, or is it more humid on a 40-degree day?
If you decrease the amount of temperature, then it should go down?
Absolutely. If you're asked to find the pressure at a temperature that is lower than boiling point, then the vapor pressure should be lower. If you're asking to find the pressure at a temperature higher than the boiling point, then the pressure should be higher. They are directly related. So when you solve your question, when you solve your 2-point equation, if you don't have that direct relationship, redo your calculation because you've done something wrong. The other point in the manual I want to point out is on page 120, which is this data table. You're given the vapor pressures and the temperatures. Take these numbers, make them into ln's. These numbers, make them into 1 over t's. Then you're graphing these versus these. Question about that part of it? Okay, other thing. He has a link in the experimental page. There is a link. If you didn't like my explanation of the calculations, try Dr. Musgrave's, okay? I'm sorry. Hold on one second. I'm trying to find the data. You go to the very end here, I think you're going to find it. There we go. There's not much there, guys. Yeah, they don't use exactly 760. They use 760.2. You need the boiling point to get the heat of vaporization for the 2-point thing. And you find that in the student data for labs. Do you want me to go over the actual results or not?
It couldn't hurt to just go over them.
Well, let me ask you this, guys. I asked my other class this and got one response. My going over the results section with you, has it been just added time that you didn't really need, or has it been beneficial? I'm asking because I need to know whether it's useful for me going over this stuff.
Yeah, I think it's useful because you kind of like, it doesn't give us any surprises.
It helps
Going
us
ahead.
understand what we need to be looking for as well.
Well,
Exactly.
I really don't want to surprise you guys. So that's why I've done this. So if you don't like it, I apologize, but this is what we're dealing with. Okay. Question 2, boiling point. Just copy it over from the student data. All right. Change it from Celsius to Kelvin. Record the atomic pressure. That's 760.2 goes in there. Just copying some data from one point to another. Second question. Determine the vapor pressure of your unknown at 295 K. One equation doing that. Fourth question. You got to upload a graph, whether it be hand-drawn or Excel, I don't care. If you do a hand-drawn graph, then I do not want you to use any of the data points as your calculation of slope. So remember, I want labels on the axes. I want labels for the title. Don't worry about if you are doing a hand-drawn graph, then yes, you're going to be you're going to be responsible for A, and make sure they're not data points. If you are just doing the Excel graph, I want you to put the equation for the line as A. Then for B, I want you to solve for the heat of vaporization. There's the formula there. And that's it, guys. As I said, not a whole lot to enter in for this week. Questions about the results section? All right. Post lab. Basically, in the post lab, you're going to be doing Claussius Clappeyon equations. I think 3 of them, if I'm not mistaken. Preview. Okay. This is a hard one, guys. He gives you the known value for the heat of vaporization, gives you the experimentally determined value and the formula. Determine the percent error. Now, looky here, guys. You're going to be subtracting 44.01 and 44.44. How many significant figures is that going to have?
Should that be 4 significant figures?
Nope. How far past the decimal
Oh,
are you going to
2?
have to go? Come on, guys. I'm helping you out here. Don't waste my time. Somebody yell out how many places past the decimal you have to go when you subtract 44.01 and 43.44.
Is it
2.
2?
2.
2.
I said, oh, my mic didn't pick it up.
Sorry, Samir. 2 places past the decimal. Okay, so are there going to be any numbers to the left of the decimal?
No.
No. So how many significant figures? How many significant figures is the numerator going to have?
2.
So if the numerator has 2 sig figs, how many significant errors
3.
is the percent error going to have? If you get it wrong, then it's on you. All right. Question 2 gives you normal boiling point. Normal boiling point, when you're doing these equations, associate the normal boiling point with atmospheric pressure 760. Gives you the heat of vaporization. Asks you what the vapor pressure is at some other temperature. In other words, question 2 is the same employment of the Claussius Clappeyon you just did in the experiment. Question 3, another Claussius Clappeyon, except it gives you a temperature with a vapor pressure at it. And it gives you the heat of vaporization. Now, what may seem a little bit funky looking at this, it may seem like you don't have enough information, but you do. Because you know at boiling point, the pressure is 760. So in this case, in this problem, you have two pressures, one temperature. Solve for the other temperature, which is the boiling point temperature. Any questions about the lab, guys?
Looks good.
All righty. So I'm going to look at the final now. Saki, you didn't remind me.
You figure out before I'm gonna say
Okay.
it.
I'm going all the way down. I'm going to hopefully find the final. Okay. Now, I'm going to do this. I'm going to show you some of the questions. The reason I'm showing you some of the questions is the numbers aren't in there. The other reason I'm showing them is right now, I am going to stop share for a second. I'm stopping sharing, so I am